This is the last question in the Unit 2 worksheet 2, and we'll start reading. It says, kicking a football, a ball is suspended from a ceiling by a string of 7.5 meters. This is important because from this we're actually going to have the radius. As that ball goes around, it's going to have that will be the radius. And the ball is kicked horizontally and it rises to 6 meters. Okay, so the first question, assuming that air resistance is negligible, show that the initial speed of the ball is 11 meters per second. Now what's happened here is that he kicks and he gives this ball a certain kinetic energy, and it goes up to this point over here where all that kinetic energy changes into potential energy. So we can work out what the EP is, and that will work out to be the kinetic energy. So that's going to be mgh. So the ball has a mass, and actually we don't really have to worry about the mass because that's going to equal half mv squared, and we can see that the masses actually cancel out, which makes that very convenient. So the v squared is actually equal to 2gh, and I find the square root of that. That will actually give me the v. So we're going to have the square root of 2 times 9.81 times by 6, and if I do the square root of that, the square root of 2 times 9.81 times 6, close brackets, enter, I get to a value of 10.85 about. But notice here that all of these are given in two significant figures, so I'm going to change this as 10.85. I'm going to change this into 11 meters per second to -1, write my answer in two significant figures. Now it says the mass of the ball is 0.55 kilograms, and the impact time, the kicker's foot, is 150 ms. Now remember, this m over here is a millisecond, so that's actually 150 times 10 to the -3, so that's actually going to be 0.15 seconds there. Estimate the average force exerted on the ball. So here we'll obviously use our impulse, that the F times the change of t is equal to your change in momentum, which is equal to mv minus u. The ball was stationary to start, so your force is going to equal to be 0.55 times by my 11, this over here, and divided by the time. This initial velocity was 0, so we can cancel it out, and that's 0.15. So in doing that, we get to about 40 newtons. Now, next question here is quite an interesting one. Explain why the tension in the string increases immediately after the ball is kicked. So just before the ball is kicked, the tension basically is equal to the weight, mg. But immediately after the ball is kicked, it also has to provide a force to provide for the circular motion, which is mv squared over r. This is to provide for the change in direction of the ball. So this is a force towards the center, and it provides that force to be able to do that, to cause that acceleration towards the center, to provide the acceleration that takes place. So I'm sure you'll be able to write that. and therefore calculate the tension in the spring immediately after the ball is kicked. So we've got our formula that I've written up there. It's going to be the mass, which is 0.55 times by 9.81 plus 0.55 times by 11. And now remember, we're going to divide not by 6 but by 7.5, because 7.5 was actually the length of the string. 7.5. And when we do that, we get to a total that's about 14.4. But again, I round down to two significant figures, so I get 14 newtons. And that's it for that question. So any further questions, please come and see me and I can explain that further for you.